Okay, next we are going to discuss about isomer shift in mass spectroscopy. One of the method for measuring the gamma ray transmission is the function of Doppler velocity. Suppose സോഴ്സും സാമ്പിളിൻ്റെയും സോഴ്സിൻ്റെയും ഡിസ്റ്റൻസ് അറേഞ്ച് ചെയ്ത് സപ്പോസ് സാമ്പിൾ ഒരു പർട്ടിക്കുലർ ഡിസ്റ്റൻസിൽ മൂവ് ചെയ്യുമ്പോൾ നമുക്ക് സ്വാഭാവികമായി അതായത് പർട്ടിക്കുലർ ഡിസ്റ്റൻസ് അല്ലെങ്കിൽ പർട്ടിക്കുലർ വെലോസിറ്റിയിൽ മൂവ് ചെയ്യുമ്പോൾ നമുക്ക് കിട്ടുന്ന കൗണ്ട്സ് പെർ സെക്കൻഡ് ഓൾമോസ്റ്റ് കോൺസ്റ്റൻ്റ് ആയിരിക്കും. ഒരു പർട്ടിക്കുലർ വെലോസിറ്റിയിൽ സാമ്പിൾ അതിൻ്റെ അബ്സോർപ്ഷൻ പീക്ക് കാണിക്കുന്നുണ്ട്. ദാറ്റ് ഈസ് ഇവിടെ നമുക്കൊരു ട്രാൻസിഷൻ സ്പെക്ട്ര ഇവിടെ നമുക്ക് ഇവിടെ ഒബ്സർവ്ഡ് ആണ്. ആ ഒരു പർട്ടിക്കുലർ വെലോസിറ്റി കഴിഞ്ഞ് വീണ്ടും നമ്മൾ മൂവ് ചെയ്യുമ്പോൾ നമുക്കിവിടെ ഒരു കോൺസ്റ്റൻറ്റ് ഒബ്സർവേഷനാണ് ഇവിടെ കാണിക്കുന്നത്. ഓക്കെ, അപ്പോൾ ഈ ഒരു പർട്ടിക്കുലർ വെലോസിറ്റിയിലാണ് അതിൻ്റെ ട്രാൻസിഷൻസ് സംഭവിക്കുന്നത്. നമ്മൾ ഈ ഒരു ട്രാൻസിഷൻ സ്പെക്ട്ര വെച്ചിട്ടാണ് നമ്മൾ ഇതിൻ്റെ ഒബ്സർവേഷൻ കംപ്ലീറ്റ് സ്റ്റാർട്ട് ചെയ്യുന്നത്. ഓക്കെ, ഇൻ മോസ്ബർ എക്സ്പെരിമെൻറ്റ് സപ്പോസ് ഇഫ് ദ എൻവയോൺമെൻറ്റ് ഓഫ് ദി എമിറ്റിംഗ് ആൻഡ് അബ്സോർബിംഗ് ന്യൂക്ലിയർ ആർ എൻറ്റയർലി ഡിഫറെൻറ്റ്, the energy of the nuclear transitions is zero may differ by a small amount. This energy difference is known as isomer shift or chemical shift. It may be positive or negative depending on the electron cloud. Okay, suppose here this transitions this shift is towards, suppose there is a negative shift, but here the shift is in the positive related to the zero. So the isomer shift is what do you mean by the isomer shift or chemical shift? It is the shift or it is the energy difference between the nuclei if the environment of the emitting and absorbing nuclei are different. Okay, actually this isomer shift arises because of the nucleus of the atom is arise from the electronic environment. Okay, if this electrostatic interaction between the nuclear charge distribution and electron charge distributions are different from nucleus to nucleus, depending on this electrostatic interactions between the nuclear charge and electron charge distribution. Okay, this electron charge depending on this electron charge distribution or this environment, this shift is can be written as, that is delta E is equal to 2 pi by 5 Z E square R square psi of 0 square, where psi of 0 represents it is the total electron density at the site of the nucleus. Actually this electronic interactions, that is electron charge distributions, is the main contribution is from the s orbitals, because it has direct interactions with the nucleus, and also the p orbitals have the indirect interactions with the nucleus, because these outer s electrons have the direct interactions with the p orbitals. So it has the interactions with the nucleus is in the indirect form. So the main contribution is from the s orbital electrons. Okay, so we can find out delta the change in delta E, that is the change in the excited states and ground states. So we can write that is a 2 pi by 5 Z E square psi of 0 square R square minus R square, that for the excited and ground state. This difference that we can again written in the form of the radius of the equivalent sphere of uniform charge distribution. R is the radius of the uniform charge distributions if we consider it is in the form of the sphere. So this difference is 2r dr, and again we multiply and divide r, that is 2r squared dr by dr. Okay, now we can replace this term by 2r squared dr by dr. So delta we can write this is in the form of 4 by 5 z e square r square dr by r psi of 0 of absorber and psi of 0 square of the sample. See, this is the ground state, this is the excited state, and due to the change in the electronic environment or due to the change in the electrostatic interactions between the nucleus and the electronic charge distribution, so this is the change in the ground state, and here is the change in the excited states. These ground states and this change in the energy of the ground states and this change in the energy of the excited states may or may not be equal. That purely depends on the electronic contributions or electronic environment of the nucleus. That depends on the atom. Okay, that is different from one to another. And now this from this point of view, this the terms, that is r square dr by r, that is this isomer shift, that is delta is the isomer shift, that is depends on r square dr by r, where r is the radius of the equivalent sphere of uniform charge distribution. Okay, here we will get, it is a constant term. Okay, so it is a constant for a given MOSFET transitions, and another chemical term is a psi of 0 square for the absorber minus psi of 0 square for the sample, and this term represents the difference in the total electron densities at the absorber and at the source nuclei, not sample, source nuclei. Absorber is the sample, so that's my mistake. Absorber is the sample and is for the source. Okay, so psi of 0 for the square for the absorber and for the source. So this is the difference in the total electron densities at the absorber level and for the source level. And sometimes we can say this delta as the chemical isomer shift. It may be positive or negative. If it is positive, that is dr by r is the positive, that is we can conclude the psi of 0 square for the absorber that is greater for the psi of 0 for the sample. Okay, that is this chemical isomer shift of two different resonance in the same series of compounds is interrelated by the contributions of the dr by r. See, this is the examples for the two compounds. That is one compound is a zinc telluride consisting of 129 mass number telluride, and here 127 mass number. Here this is the energy difference. Here this is in the negative shift, that is related to the 0 position, but here in this compound we can observe there is a positive shift. Okay, and also we can observe this full width, the half maximum of this compound is very low compared with this one. Okay, it is very sharp, and here this is a broadened peak, not peak, broadened depth. We can observe broadened transitions, not peak or depth, it is the broadened transition. Here it is the resonance transitions, or it is the sharp transitions we can observe. Okay, this chemical isomer shift, it is the MOSFET parameter that gives the maximum amount of the chemical information. Okay, determination of this chemical shift allows estimation of the relative s electron density, which in turn gives an idea of the bond character of atoms or ions. Okay, keep it in mind that this this isomer shift is mostly contribute from the s orbitals, so it has the direct interactions with the nucleus, and also the p orbitals, d orbitals, f orbitals, it has the interactions, but it has the influence only in the indirect mode. So the outer s electrons has the interactions with the p electrons. So we can say, or we can conclude, this p electrons has the indirect interaction with the nucleus. Okay.